Good morning, everybody, and welcome to a bit of DNS. Now, there it is, DNS, the domain name system. What is it? Well, it's just a way of giving names to devices. So that's all domain name system is. It's a way of taking a device and giving it a name. So let's just see what's going on. Let's imagine there is somebody here sitting at a machine and they're typing in, they're surfing the web, and they've got a web browser open, and they type in something like www.bt.com. Now, they're going to have to go to the web server. So let's imagine that this over here is actually the server. Now, if that's a web server, it's going to be running the HTTP service. And you know that HTTP listens on TCP port 80. So that means what will happen, we will get some HTTP GET request, which will be wrapped inside of TCP. And there will be the destination port of 80. There'll be a source port of some random port up at the top level, so 51111. That gets wrapped inside of IP packet. At the front of the IP packet, we've got the destination and the source IP address. Well, this machine will certainly know its own IP address, so it could have an IP address of 1, 2, 3, 4. Now, the IP address waiting here on this machine, that IP address could be something like 2, 3, 4, 5. So they certainly know their own source, but the problem is the user only typed in the name. That's a domain name. They didn't give an IP address. So how does the machine, the IP system, manage to fill out the destination IP address there? Well, the situation is that out there on somewhere out there in the internet, we do have our DNS servers. Now, what's the job of a DNS server? Well, a DNS server will, what we say, resolve domain names into IP addresses. So the whole topic is name resolution. So without name resolution, this machine will be unable to find the destination IP address. So that machine would have to go out to the DNS server with what we would call a query. So it will go out with a DNS query, and it will just say, please, can you, for www.bt.com, what's the IP address? Now, the DNS server hopefully knows that and will send back a DNS answer. So we will get coming back an answer, and that will just simply say, oh, you asked me www.bt.com. The answer to that is 2, 3, 4, 5. So that's the role of the DNS server. It resolves domain names into IP addresses, and that is called name resolution. Now, we can call these boxes DNS servers, but another name, which is exactly the same, is name server, or just NS, a name server. Some people call them DNS servers. Some people call them name servers. They do the same thing. Now, if I just show you here quickly a little Wireshark, I'm sure you all know Wireshark Traffic Analyzer. Here we have a DNS query going out, looking for www.snt.co.uk. And then from our DNS server, we're getting a standard query response. And inside there, you can see there's an answer. And it's saying, there's the IP address there. So that's the IP address we're looking for that belongs to snt.co.uk. In fact, you can see that what it's giving us is actually two pieces of information in the answer. It's actually saying, well, when you asked for www.snt.co.uk, actually that refers to snt.co.uk, and we've given you that snt.co.uk is that IP address. So that's a standard query and response in DNS. Notice that the destination port for this query would be 53. And so when it comes back, which is what we can see the answers coming back, it's coming back from UDP port 53. So DNS will sit there listening, UDP port number 53. Now, you can have DNS also listening on TCP port number 53 in certain situations. Now, domain name system. What can you have in a domain name? Well, first thing you've got to know is that it is not case sensitive. So uppercase, lowercase, not important. Now, you can split that domain name into sections, and you know that those sections are separated by a dot. And what are you allowed to have in those sections? Well, you're allowed the very traditional LDH. That is, you're allowed letters, you're allowed digits, and you're allowed hyphens. Now, you can have in here a maximum of 63 characters. And the whole thing from beginning to end will, in practical terms, be 253 characters long. So that's what you're allowed to put in a domain name: letters, digits, and hyphens. Now, if you think about that, that kind of does say that, well, we're only in an English or Roman alphabet world. What about all the people who live in different parts of the world who speak different languages which use different lettering and scripts? Well, there is a system for internationalized domain names, and these can include non-ASCII text characters. For those people who remember ASCII, ASCII is our old plain text, very simple, which was the original definition, just letters, digits, and hyphen. Those are plain old ASCII. But if you want to use a special character, then you're probably going to use something like Unicode. Now, Unicode will include all kinds of characters. For example, you might have an umlaut or something like that. Now, we need, when we're doing an internationalized domain name, we have to convert that umlaut into ASCII, because all domain names are ASCII, so we need to convert that, and there's a special method to convert it. It's called Punycode. And you can see here we've got Munich in German, München. There's our U with an umlaut. If we use Punycode to convert that, we get this, which you'll agree is all ASCII text, and so truly that would be the domain name. Now, what's happening here is that this here is actually saying put the U in the second position. So the second position could be here. There's the second position. So that is telling us to put the U in there. So these are internationalized domain names. So you can have domain names in any characters, and you can even have some top level domains which are internationalized. Here's a few examples I stole off Wikipedia, and you can see that we've got various scripts down here. Japanese can be converted into ASCII using the Punycode system. You also notice there's an emoji there, and we'll talk about that in a second. Now, I typed in to my web browser XN. Now, XN is the indicator that this is a Punycode conversion. So that is put in front, and that means this is a Punycode conversion. Now, I've typed in that into my web browser, and sure enough, a web page came up. Some hoster is trying to sell me that domain name. Here's another one. This is dot, and this is for Hong Kong in Chinese characters, which if you put it into Punycode comes to be that there. And if I go out and search for the name servers responsible for that domain name, you can see I can go and put in the Punycode into my little dig utility to go out to DNS, and it's found all the name servers, so it's actually worked. Now, what about emojis? Because emojis can be converted using Punycode because it's just a reference number, really. Now, there are problems with emojis, and they're kind of discouraged. The problems that you can get with emojis is they can be very similar to each other. So looking at them, you don't know which one it actually means. So reading a domain name in emojis can be problematic. The other problem is people from different places in the world. What about the skin tones? Are we displaying in a universal yellow? So there's things like that. And the problem also is browsers uneven in how they show. So there are problems with emojis. Now, you can get emojis registered. They're discouraged, but some registrars, the people who accept registrations, will accept them at the second level. And I'll explain what second level is in a minute. And an example of those would be .ws, which is Western Samoa. They accept them. And there is LA, which is Laos. I think they accept them as well. So you can get them wedged into your domain name if you really want to. Now, who controls all of this? Well, it's all controlled by ICANN, which is the Internet Corporation for Assigned Names and Numbers, and they coordinate domain names, IP addresses, port numbers, but they don't actually do it. When ICANN is really just all about the policy. So they'll set policies, but they don't actually do it. Who does it? Well, from a functional point of view, who performs the functions? Well, there's IANA, the Internet Authority for Names and Addresses, and who controls them? Well, it used to be ICANN, but now they are controlled by PTI, and PTI is supervisor of the operations, so their operational supervision. IANA actually do it, and ICANN do the policy. So we've got a bit of a chain of command there. So that's the regulators and the people who make sure it all works. Now, if you want to get a domain name, then if we think about an example, so think about .com. So .com is managed by the registry that has the contract from ICANN to be the official supervisor of the .com top-level domain. Under there, you will get registrars. So you go to them if you want to rent a .com domain, and so you are down here as the customer. This is you. You go to the registrar interacts with the official registry, and they are the source of all knowledge for .com. Now you can register your own domain names if you want, so you could come up with super duper, but you'd have to go to ICANN and you'd have to give an application to ICANN for the super duper domain, and you'd have to justify it and say that you are responsible enough to manage it correctly. So that's the chain of command and the organization. Now, in reality, this is a big tree. So you can see that it's all anchored at the top. The domain name system is a big tree, and at the top of the tree is the root. Then underneath the root, we've got things like .com, .org, .net, and these are called our TLDs. So that would be our top level domains. So those are our TLDs. Now there are many of them. You can also see that we've got our country code top level domains over here. So these are country code top level domains, and these over here are called generic top level domains. If we go underneath .com, you've got BT, Asda. I have no affiliation with these companies, by the way. It's just short names are good for diagrams. So bt.com, that would be called a second level domain. Now, it's all organized in a tree, and that tree is all anchored at the root. Now, if I do have a box, so we can say down here, off here is a machine, and we'll call that server 1. Now, if I want to give that a full name so it's unique in the world, then don't forget it's all anchored at the root. So what do? We come and we walk from the root down the tree until we get to that box to build up what we call a fully qualified domain name. So FQDN, fully qualified domain name, and it's anchored at the root. Then we've got our com, then we've got our BT, then we've got our corp, and then we've got SRV1. That is our fully qualified domain name, and that uniquely identifies that box in the DNS tree naming system. Now, the COM is all controlled by a registry, and the registrars, if you go to one like GoDaddy or 123.reg, they can sell you your second level domain name, rent it, you can. Underneath, you're responsible for creating that tree structure as you see fit. So for example, I've got BT here split into two subdomains, Corp and HR, and that's completely at the will of BT. They design their own subdomain below in the tree. Now, there are some of these top-level domains that are reserved, such as test, example, invalid, localhost, for special purposes, for testing, for doing examples, and so you can use these to play around if you want to. There's also some second-level domains that are reserved. Example.com, these are reserved just for examples and people playing around. So we've got to think about name servers, and if we're thinking about a name server, is there just one name server in the world that knows all names? No. So what you have is inside a name server. So if we make this into a name server, inside a name server, there will be a file. And that is just a text file. And that is called the zone. Now, what is a zone? Well, a zone is a piece of the DNS namespace. So for example, we can say our name server is going to be responsible for this piece of the DNS namespace. So that's going to be our zone. So this would be a name server, and that zone there would be the zone which would be responsible for bt.com, and strictly speaking, we put that on the end. Now, inside there would be all the information on all the machines. So those are names inside that zone space. So a name server has on it zone file, and that zone file is responsible for a piece of the DNS namespace, because it would be impossible for a single name server to know everything. Now, if I ask this particular name server, for example, if I said, oh, do you have the record for www.bt.com? And indeed, it does have an IP address, 2.3.4.5. So if I ask this name server, do you know www.bt.com? It replies, yes, I do. That name server got that answer from the zone file. So if a DNS answer, if you get an answer from a name server which has a copy of the zone file, we say that that answer would be authoritative. I think I might have spelled that wrong, but I'm not going to dwell on that. It's authoritative. So if you get an authoritative answer, it is from the name server that actually has the zone file on it. Now, when we're talking about zones, then a zone must be, when you make a zone, so we've had this as a zone, and that's all good because it's all completely connected within that bit of the space. You cannot do this because you can see that that would not be allowed, because we say that is discontiguous piece, oh, my spelling's going a bit today, piece of the namespace. So your zones must be contiguous, meaning it's all connected inside of the zone. You can't have a bit of this tree branch of the tree here and a bit of this branch of the tree there. Now, let's have a look at where the name servers are. So there will be possibly a name server that is responsible for this. There'll be a name server that's responsible for this. And there's a name server responsible for this, because there's no single name server that knows everything. Now this would be a root name server. Now this is the .com name server here. So that's the com name server, and this is the bt.com name server. So you can see that there is no single machine knows everything. So we've got a name server up here, we've got another name server here, and we've got another name server here. So there are name servers all around, all responsible for a little bit of the namespace. So let's see what happens on a typical DNS query. Let's imagine that here is somebody sitting and they type in the name www.bt.com. That will cause a DNS query. Now, where will the DNS query go? It'll go to the configured DNS server on that machine. Now, where will that machine have got its IP address and all its details from? They would have been picked up from DHCP. So DHCP would have told it what its DNS server is. Now, the DNS server is going to be this one here, because when you're inside a corporation, usually there will be some kind of local DNS server. So we're going to get our DNS query that goes out to our local DNS server, and it's just going to be saying, do you know www.bt.com? Now, if that's my local name server, it won't have a copy of the zone and it won't know. So how is it going to find out? Well, we know there is everything, it's a tree, and everything is anchored at the root. And we know there's a name server up at the top responsible for the root. So what we do is we go out to the root name server. So we come up to the name server for the root, and we say a DNS query, send it out. So it'll go out just with the same query and say www.bt.com. Now, this root name server won't actually know that, because that information will be down in the bt.com name server. But the root server knows where the com name server is. So the root server will just reply and say, don't ask me, go to the com server. So the reply is simply go to the com name server. Here is the com name server. So this is the com name server here. So here is the com name server. Now our local DNS machine goes out with the same question. Do you know www.bt.com? What's the IP address? And it says, nope, sorry, but I do know where the bt.com. So that will just say go to bt.com. Now, when these referrals, it will be to the name server that they're referring. So go to the bt.com name server. And then down here, we have the bt.com name server. And finally, our local DNS server goes there and it does ask the same old question. www.bt.com, and of course it knows the answer, so it looks in its zone file. So inside the zone file it will find www equals 2345, and that answer is then sent back here. So now we finally got our answer, www.bt.com equals 2345. Now this here is a resolver. So this is a name server, and we'd call it a full resolver because we send it a query and it'll go out and do the full name resolution and come up with the answer. Now, clearly it doesn't want to do that every time. So there will be, on that machine, there will be a DNS cache, and it will take that information and go, okay, www.bt.com equals 2345, and it will store that. It finally gives the answer back to this machine, which also will possess a DNS cache so that it doesn't have to ask again. So that information goes in there as well. So that also has a local cache. And you can see caching is great because it means that we're reducing the amount of DNS traffic on the internet if we have lots of caching servers local, so that we don't have to keep asking the same things again and again. Now, this root name server, who's responsible for it? Well, we did say that ICANN and then PTI and then IANA. There's a nice website, rootservers.org, and you can see there are many root servers all around the world. And so there are 101,097, it says here. Now, they're not all individuals, because on this website, you can see that if I go to the map and expand it and look at London, you can see there's an A root name server, a couple of F's, and you can see that the root servers are actually A, B, C, all the way up to M. There are actually 13 root servers, but they are cloned and replicated and placed in lots of different positions in the world for redundancy and failover and efficiency. The I root server is run by NetNod, and you can see they've got them in Amsterdam, in Tokyo, Sao Paulo, and all of those root servers, all of the I root servers have exactly the same IP address, which kind of breaks a lot of rules that you may have been taught about IP addressing, but they've all got the same IP address. Now, what does it mean here when it says local and global? Well, this is all to do with the BGP announcements of the presence of that IP address. And if it is a local, it means that BGP is announced locally only, So if it's local, there is BGP advertised only to near networks. If it is a global instance of the root name server, then it is advertised by BGP to all the world. And you can see some of them do IP version 4 and some of them do IP version 6. Now this system is called anycasting. And what is anycasting? Anycasting is multiple instances of same device providing same service, and we rely on routing takes us to the closest. So we've got many root servers, all with the same IP address. The I's have one IP address, the G's have another IP address, and it's called anycasting. So for example, here we've got the F root server, that's the IP address for the F root server, and under normal conditions, BGP will advertise the presence there. This will be advertised, and it will be advertised there, but the router here, inside its routing table, will always prefer to send traffic to the closest instance. So even though it knows that there is another availability of that exact same IP address in a different direction, it will take us to the closest one. Now, if one of those, if that were to fail, then because it has received the BGP advertisement saying that that identical copy is available somewhere else, then the DNS can be sent over. And that is anycasting, where you have multiple boxes with the same IP address, and it's the routing tables that will take you to the closest available one. Now here, I'm using this utility on Linux called dig, and I've dug and I've said get me snt.co.uk. So this is what I'm looking for here. This is my query. I want to find the IP address for that. And this trace is saying, show me what you're doing. So you can see that the first thing it goes out to do is to find the root servers. So here it has found the root servers, so the root name servers. Then it chooses one of the root name servers, and you can see here that it's chosen this one, the L root server. It goes out to the L root server and says, hey, do you know snt.co.uk? And that L root server says, no, but please go to the UK name servers. And there are the references. If you want UK, here are the name servers, please go and ask UK. Then we have taken one of those. We've taken this one here, and we've gone out and we've said, do you know snt.co.uk? And that has come back and said, that has come back, there it is, that one there, that UK name server has come back and gone, please go to snt.co.uk name server, which we can see is down listed here. There's the available ones. And finally, we go down and we ask that name server that comes back and it says, yes, there is your final answer that you're looking for there. Now, this name server that replied also told us all the name servers. So that's indicating to me that that was an authoritative reply. So what we said earlier, that you go to the root, you get passed down, you get passed down, you get passed down, is actually borne out here by my Linux machine doing exactly that. If we think about the format of a message, I don't want to dwell too much on this, but you've got header, then you've got a question, answers, authorities, additional records. So that's the format of a DNS message, and this is the header, and it will say what's going on in that message. Is it a query? So this bit here is indicating if it's a query and what kind of query here, what kind of answer it is. And one thing I will point out is here we've got recursion desired. Now, what is recursion? Well, if we go back to my explanation here, this name server is performing recursion, which means that it will go out and get the answers for you. So this is recursive name server. So when that question went out, we did set on it the recursion desired bit and said, if you can do it, please go out and get the answer for me. These name servers here, and these are authoritative name servers because they have the zone on them, they do not do recursion. They will just refer you to somebody else, whereas a recursive server will go out and do the job for you. Good. Now, we did say that a name server has on it a zone file. So there's the zone file on the name server. What's inside the zone file? Well, inside the zone file, we have multiple resource records. So these are resource records, RR, inside the zone. Now, you know that when you want to find something, you may want to find the address. So an A record, that would give you a name to IP version 4 address. Now this is quadruple. So IP version 4 is 32 bits, quadruple is 128. This would be a IP version 6 address. So in your query, you would say, okay, I want www.bt.com, but I want the quadruple A record, please. Do you have any IP version 6? Then we've got MX. Now, MX is the mail server for that domain. If I wanted to send an email to somebody working at snt.co.uk, I'd go out to DNS and I'd say, do you have the MX record for snt.co.uk. Now I could just demonstrate that to you. I could dig it out. I could go dig snt.co.uk, give me the MX record, and give me a short answer. And hopefully, there it is. So it is snt-co.uk mail protection outlook.com. That is the name of the mail server. Notice that what it provided, an MX record, will just give you back another name. So that is a name that's returned to you, and you'd have to go and do an A record lookup to get the IP address. CNAME, well, a CNAME is just an alias, so it points to another name. So when you ask a record, it might come back and say, oh, here's the CNAME, and that just points to another name, and then you have to go and find that name. Name server, well, you know what that is. That is, give me the name server for the domain. And you can get text records, and that's just some information, and I'll just show you an example in a minute. And then there's the SOA record. Now that's very important. That is our start of authority. And that can give you some info on the zone, mainly used by other DNS servers. If I do a quick dig, and I'm going to dig, and I'm going to go to google.com, and I'm going to say any records you have on that. And you can see it's got some A records for google.com, IP version 4 addresses. We've got some IP version 6 quadruple A records. We've got an SOA record giving us information about that zone. And here are the mail servers for google.com, and you can see they're giving us other names. And we would have to go and look up those names and get the IP address. Here's a text, and it's just something that some people might like to know, so they might search for that. And there you go. So those are some of the records that I've just talked about. Here's an example of a CNAME. So www is actually an alias for ubu18-1, and there we have an A record for ubu18.1, and there is the IP address. So a CNAME is just a name-to-name mapping. It's an alias. MX records can come with numbers. If we do just a dig out on the MX records for Google, you can see there's numbers there, 10, 20, 30, 40, 50. This is a preference. So this is a priority preference which they would like you to use when sending mail. And the lower is preferred. So that is lower preferred. So but if you can't get through to that one, go up to a 20, and of both of them, if they are 10, then you can round robin between them, send one mail to that one, another mail to another. But if none of the 10s are available, go to the 20, then go to the 30. There are also these things called Srv records. Now you can see here that I said that it was letters, digits, and hyphen. Here we do have an underscore. And that's allowed in these special records called service records. And with service records, what am I looking for? I'm looking for a particular service. And here I'm looking for the SIP service. Now, many of you will know that SIP is used for VoIP. So if I wanted to make a VoIP call to snt.co.uk, I would have to find the SIP server. So I can go out to DNS and say _SIP, find me the SIP server, _UDP, which uses UDP as its layer 4. And then it can come back and it can say, there it is, there is the machine you should go to if you want to do a VoIP call. You can see there's some numbers there. Again, this is a priority, just like in the MX records. This here, you will notice, is a port number, and many of you will recognize that as the standard SIP port number. And then we have here, this is a wait, so if the priorities are the same, this is a wait, and higher is better. So that's service records. Now, if you want to do a bit of manual DNS name resolution, there are two commands, Nslookup and dig. They're usually available on most machines at the same time, but if it's not on Windows, it's easily, generally it was dig for Linux, and Nslookup was the one you'd find on Windows, but now you can find them on both, usually both on the same machine. It's easy to install dig onto a Windows machine if it's not there. And so you can specify the type of record you want and the domain. You can even specify which name server you want to query. So that's Nslookup, and there's dig, very similar thing. You can specify the name server, short answers, and you can do reverse lookups as well. Does Nslookup or dig use our locally cached information? And this is important, and it is no. So if you do a dig or an Nslookup, your locally stored DNS cache is not referenced. It will go out to your configured name server. Now, negative responses. What if you go out and you do a query for a name that doesn't exist? Well, you get two kinds of response. You will get an NX domain, no such domain. Now, if that comes from the authoritative name server, then they will send you the SOA record, which is that domain zone information record for the parent zone. So that's negative responses. So if you ping a non-existent domain, do you get a response? Well, you will get a DNS NX domain. Now, are we going to put that in our local cache? And the answer is yes. So if you go out to DNS and you get a negative response, you do store that response so that you don't have to go out again. Here I am digging for a non-existent domain. I get a negative answer come back. Here, I actually did it on the authoritative server for .com. That's an authoritative name server for .com, and they sent me the SOA record. Whereas this wasn't done to an authoritative server, this was done to a caching server, and a caching server is one like I described before. Here locally, it has no zones. It's just a caching server acting as an intermediary. Right, we've got to nearly 11 o'clock, and we're just going to have a quick 5-minute break. So I'm going to come back in 5 minutes. This will allow you to get a cup of coffee and use the restroom if you want to. So we'll be back in 5 minutes. Right, welcome back everybody, and let's carry on with DNS, our favorite naming system. So we've talked about name servers and how name servers will resolve domain names into IP addresses. You don't have to go out to a name server. There is this thing called a host file. And what is a host file? A host file is a local static file. And inside that local static file, we have names to IP address mappings. So where would you do that on a Windows machine? Well, in a Windows machine, if you go into the Windows System 32 drivers, etc. Now, I've got mine open here. Here is the hosts file. And these are comments with the hashes here. And you can see I've put in there 1111 is mapped to Harry. I've saved that. And so now if I were to ping Harry, you can see Harry is being resolved to 1.1.1.1, the Cloudflare DNS server. And where did it find that? It found that through using this hosts file. So the first place it will look really is in the host file before it ever goes out and queries the DNS. Now, you might say, well, what use is that? Well, you would use this in a situation where you can't allow machines to go out to a DNS server. So this would be used on enclosed networks with no DNS server. Now, don't forget, if you do have a DNS server, that is a point of failure. So if you're running in an enclosed network with a single DNS server, if that goes down, you've lost all your name communications. So in certain secure systems where they don't want outside access, but they don't want that possibility of failure for name resolution, they will put a hosts file on every device in that network. Obviously, it's a bit more administrative effort to update it, but there you go. So that's a host file. Forwarders. Let's think about a forwarder. So if I do have this situation here, where this machine is sitting on the border between the public and the private. So here is our private world, and this is the public world. You may not want internal name servers. So let's have a name server here, a name server here, a name server here. You don't necessarily want them all to individually go out and do searches in the public domain to look up names. So we could configure the internal ones as forwarders and caching. So this here is going to be a caching name server. So all of them will be caching name servers. They will have no zones on them. And if any queries come in, all they do is they forward. So these are DNS forwarders. So any queries that come in, they just forward to another name server. And they have to be configured with the IP address of the name server to forward to. And then this name server here is the only one that's allowed to go out onto the public internet and do the DNS. It means that all these inside our caching, it makes your DNS setup more efficient. You've only got one machine going outside. It will also be caching here. And so you don't get a lot of external traffic from your internal name servers. So that's forwarding name servers. You may have a thing called conditional forwarding, so that when your request, DNS request, goes in to your local DNS server, it might be configured to forward for a particular domain. So anything for bob.com gets forwarded over here because we know that that is either the name server authoritative for bob.com, or it will go out and get it. So that would be called a conditional forwarder. And it's only forwarding for a particular domain name. All the other DNS queries might go to the outside world. So that's conditional forwarding. Now let's just have a little look at some different zone types. Now, this is a zone file that you would find on a Linux name server, where they often use bind as their implementation of a name server. And you can see right at the top is this interesting thing that we talked about earlier, which is the SOA record. So the SOA record gives us information about the domain. This here is the master name server. So this holds the original zone file, and that's where all other name servers with a copy of that zone file got their information from. So this is the master name server. This here is the responsible name, which means that if you put an @ in the middle of it, you get an email address, and if you have any queries about this zone, you can send an email to that address. We've got a serial number. Now that will go up by 1 every time we make a change. That means if I have a copy of the zone, if I compare my serial number to the master and I see that my number is lower, it means I need to update my zone. So this is a serial number, and that goes +1 for every change in the zone. Now, if we just go to this diagram here, we can say, okay, this here is our master. This is then some slave, and we can have another slave, and you can see there's a relationship here. Now, they need to update if they've got a copy of the zone, so the zone will be on there. So the zone file is going to be on the master, and there'll be a copy on the slave. Now, these are all official name servers. These are all official name servers, and those name servers would be listed here in that zone file. This will need to get a copy of that. And how does it know when its copy is out of date? Because it references the serial number. Now, how often does it go to the master and say, hey, can I have your SOA record? I want to I want to see if I'm out of date. Well, it will do that according to this here, which is 600 seconds. So the slave is going to go to the master every 10 minutes and try and update its zone. If it tries to do an update with the master, but the master is uncontactable, it will retry after 5 minutes. If it still gets no reply, that zone will expire after a week. So after 1 week of no contact between the slave and the master, the slave will then declare the zone dead and stop answering queries for that particular domain. Now, you may call this here a primary. Some people will call it a primary. And they may call these secondaries. It depends what systems you're using. So a primary and secondary. Now, it can be true that you can have your master here, which is the primary. Then you can have a relationship to here, which is a secondary. And you can have the same relationship to there, which is another secondary. Now, that's going to be a master-slave relationship there. So there's your primary. You can have two secondaries in a line, or you can have two secondaries that are actually independent. Now, how does the secondary know that the primary has an update? Well, we said that what's it going to do? So if we say this is the master and this is the slave, then what it's going to do, it's going to do a query for the SOA record. Then the SOA comes back. So then we get an answer containing the SOA. Then we can compare serial numbers. If it is out of date, so we can go, okay, am I out of date? If the answer to that is yes, then we need to do a zone transfer. XFR, zone transfer. Now, those transfers can be partial or full. So those transfers, so you could request a full transfer, which would be AXFR, or you could simply request an incremental, which is IXFR. IXFR, incremental, is just send the changes. I don't want the whole zone, just send me the changes. So that's how we get these zone transfers. Slave does a SOA query, works out if it's out of date, then it will send a request. So then it will be a DNS, and usually it'll be an IXFR request, and then we will get that come back. Now, because this can be a lot of information, this is done over normal UDP, but your zone transfers will be TCP because it is more data. Now, UDP, has a maximum usually workable maximum of 512 bytes. So they can use TCP because the zone transfer is more than that number of bytes. So that is a little about zone transfers. Now, let me move on. It is a bit laborious for the slave to keep going to the master every 10 minutes and saying, oh, give me your SOA. What you can configure is you configure notification. So you can have DNS Notify, and that means there is a change in the zone file. So we get a DNS Notify, we then get a Notify response, and then we will get some kind of transfer request. And this is push notification. It's more efficient because the changes are then replicated from the master to the slave whenever the changes happen, so the slave is then more up to date. Sometimes you don't want your master to be known to the world. If we look at this situation, this is the private, and this is the public world. Now, you might maintain your zone file yourself, and then you get that zone file replicated to some kind of external name server. So this name server is external and living out there in the public world. You actually maintain your zone file internally on a private name server. You do not want people ever to send queries to that internal name server. So we can make this a hidden primary or hidden master. And you'll see that I did tell you before that there was an SOA record, and the master name server is in the SOA record. If you've got a hidden primary, the SOA record, you can see, is NS1, the master name server is NS1 corp test, and that resolves to 1234, which is this external name server. So that's a bit of a lie. And so you can have hidden primaries, so you can maintain and keep all your records up to date, and that can be synchronized with an external name server. And this could here be provided by a professional DNS hosting service, and there are many out there, such as DNS, there's Route 53 for Amazon, Easy DNS, there's lots of them out there, FastHost, they'll all, Cloudflare, they'll all do some public DNS hosting for you. So that's hidden primaries or hidden masters. Let's have a look at zone delegation. We did say that there is root name server. So if we just go back to this diagram here, we said that there were root name servers who delegate portions of the namespace below them to other name servers who delegate portions of the namespace below them to other name servers. So this is delegation. So in the root name server, there must be a delegation telling you where the name servers for .com are. And if we look in the root zone, here's a copy of the root zone, and you can see there are entries for UK. So if you go up to a root name server asking it for a .uk name, all it will send you back is the name server records for .uk. And you will have to go to those name servers to find the name in UK, because this is a delegation. Now, when you have a delegation, so let me just get back to my slides, and let's get back to the correct place. So when you have a delegation, so if we say that, okay, this is the root here, and this is the UK, you can see that inside the root, it's got, okay, UK, go to nsa.nic.uk. So in there, it's going to say, okay, UK, go to the name server, nsa.nic.uk. So this here is the UK server, but all it's giving you is a name. How are you going to get the IP address for that name server? Well, you could go to the root name server and say, right, I've got a UK name, give me the name server, and you will end up going round in a loop. So because of this, the root name server will have to include an A record. So it will have to say, oh, and by the way, nsa.nic.uk, the A record, if you really want to find it, is. Now, if I go back to the root zone, there it is. Now, there should be somewhere a record giving me the IP address for that. And here it is. So there's the A record telling me, oh, and by the way, if you want to go there, this is the IP address. Now that you can see is 156.154.103. So 156.154.103. That record is given a special name. That is called a glue record, which a glue record gives you the IP address of the delegation name server. Otherwise, you go round in a loop. So when you do a delegation, you always have to have a glue record with the IP address of that name server so that you don't go round in a loop. So those are glue records and delegations. And you can do delegations as you see fit. So you can have a delegation for various other subdomains going to different name servers. What about reverse lookups? Now, reverse lookups are a little bit interesting in that we've talked about the DNS namespace all anchored at the root. There is a special half of the tree for reverse lookups. And its top level domain is ARPA. And then there are two second level domains, one for IP version 4, which is in address, and one for IP version 6, which is IP6. And then underneath there is every possible IP address in reverse order. So if I want if I have an IP address and I want to find the name, well, that's a reverse lookup. So what do I look for? Well, I flip the IP address over and I then add on the correct zone finish. Now this is an IP version 4 reverse lookup. And I then go out to the DNS server and I look for the pointer record for that name. So we would then do a DNS query for that name, but we want the PTR resource record. And so if we then go to the zone, so that query goes off, and here we have the contents of the zone. We've asked for 24. It goes, it finds 24, and it gives you just another name. You then have to go and do a lookup, and there is your name. So those are reverse lookups. They're actually, if you look at this, it's not an IP address. This is actually a DNS name. So they've created a special zone for textual representations of an IP address. But ultimately, all you're doing is you're looking for another DNS name. It's really pretty much a standard query, but somebody has to set up this zone to be able to answer reverse lookups. So here is just an example of a zone, which is for 192.168.1. Then we have various IP addresses within that zone, and they just give us the name. So I have an IP address, I can get the name. Now this has to be set up by the people who own those IP addresses, and it's only ever done if needed. It's not universally done. So you might do a reverse lookup and get nothing. Typically, they only do them for mail servers and things like that, where people want to do a reverse lookup for security reasons. It can be done for subnets. Here's IP version 6. IP version 6, you know, is a hugely long number with 32 hex digits. You have to flip that across, flip it over, and then put on IP version 6 up at the end, and you see 2001. There it is, it's flipped over, and you just have to do a DNS query on that. If you're doing dual stacking, which one is actually preferred? Let me just have a look at this. Okay, if you've got IP version 4 running on your machine, so when we talk about dual stacking, it means that we do have on our machine IP version 4 and IP version 6 running on the same machine. Now, if you send out a query, so if you send out a query for bt.com, www.bt.com, and the answer comes back and they give you an A record, but they also give you a quadruple A record. Which do you prefer? Well, there was something called happy eyeballs, and happy eyeballs meant that we give a preference. So happy eyeballs, this is an RF seed thing called happy eyeballs. And happy eyeballs means that when you get both of these come back, you will first try the quadruple A, but if no reply within 50 milliseconds, go to IP version 4. Now, not everybody implements this, but it's trying to get people to go over to IP version 6 by giving IP version 6 a little bit of a preference. So you first try IP version 6 to make your connection, but you're only going to wait 50 milliseconds. If they don't reply, go back to IP version 4. eDNS. Let's have a look at this. Now, eDNS are extensions to DNS. Now, extensions to DNS, obviously the DNS was all RFC'd, so everything was done, and they didn't have that much room. So what they did was, they didn't have that much room in the headers. So what they did is said, okay, what you do for your extensions for DNS is you put in, when you make your query, you put in this pseudo resource record called option. So if I make a DNS request, I add into my request this optional resource record. I put a resource record actually in the query, and that contains the extension. Because it's added as an extra resource record, it allows old DNS servers who aren't capable of the extensions just to ignore them. A new DNS server, when it receives the DNS request with including the optional resource record, will reply and include the optional resource record in the reply. Now, here's an example. We have a DNS query. Here is the additional record in the query of type opt. And what's this one doing? It's saying, okay, I'd like to do a bit of DNS Sec, please. DNS Sec can give large records. So I'm also saying, oh, don't go to TCP because it's large. Let's stay with the UDP because it's quicker and easier. And my maximum UDP is 4,000 bytes. Now, one of the things that options allow you to do is to indicate the subnet of the person who makes the request. So here I am. I'm at my machine with an IP address 1234. I want to make a request to Netflix. So that's a DNS lookup to see where the Netflix server is. I go to my server. That then sends as an option in the query my subnet. So when the name server sends the query to the main DNS, it includes my subnet. This allows Netflix to identify me as being in the UK, and when it sends the reply, that will be a UK-based Netflix server, so I go to the Netflix server that's based in the UK. And that's one of the things that eDNS can allow you to do. It can allow name servers, when asking other name servers, to include the requester's subnet. So that is the subnet of the requester. And that allows name servers who are doing geolocation to hand back the best name server, the best server providing the service for that customer. So that's one of the things you can do with these eDNS, these extensions, is the client subnet in the query. As an example, you can go to a website via Google and you can put in a name, but you can then enter a subnet and it will go and do that, and you might get different results depending on the subnet you enter into there. Right, coming to our final topic here, which is DNS Sec. What is DNS Sec? Well, DNS Sec is not about encryption. It's not encryption of DNS traffic. It's not about that. What is DNSSEC about? It is about authentication of DNS replies. And by that we mean, is it a genuine resource record from the authoritative server originally. So we know if anybody's sending us false information. And that's what DNSSEC is all about, is to stop you being fed false DNS information to make you go to bogus fake servers, such as people trying to impersonate a bank web server. How does it work? Well, it's all to do with public and private keys. So I'm sure many of you will know that there is this system where you have a private key, and then you have the public key, and the rule is lock with one, must unlock with the other. So this is called asymmetric encryption. Good. So we've got two keys, public, private key. If I lock with my private key, the only way you'd unlock it is if you had the public key. Now, because that is a public key, I can give it to anybody. It's the private key that you must always keep secure. So what's going to happen here? So we're going to take a resource record. So let's imagine we have a DNS resource record. So there is our DNS resource record, and we're going to take that and we're going to put it. So here is our DNS, here's our resource record. We're going to feed that into a hashing machine. So it goes into the hashing algorithm. Goes into the hashing algorithm, and what comes out? Out comes a special hash value, F1295. We then produce a special, so we take that hash and we put that hash into another resource record. So we've now got another resource record. So we'll put it into there. So that hashing value is taken, it's put in to, and then we take our private key. So we then take our private key and we lock it up. Now this is called the resource record signature. So this is the RR-SIG. So we have a resource record, we put it into the hashing algorithm, we come up with a hash, we take that hash, we lock it, and we put it in an RR-SIG record. And that RR-SIG record is related to that record. So now if you send me a DNS query, I can supply to you the resource record, but I can also supply to you the resource record signature. And if you can unlock that signature and compare it to the resource record, you can tell whether it's genuine or not. And this is DNS Sec. So now what's going to happen is you're going to make some kind of query. You're going to use the opt, and inside the opt, you're going to say DNS Sec OK. When that goes to the DNS server, it'll come back and it will give to you the resource record. So when it comes back, you will receive from the DNS server, you will receive the resource record, but you'll also receive the RR-SIG. So that means we've got the resource record comes back, we use the RR-SIG, comes back. What do? We take the resource record, we put it into the hasher, out pops the hash, which was F1295. We take the public key, which everybody knows. We unlock the locked hash, and out pops F1295, and you can see that these are the same, so that's a genuine record. Now all of this hinges on the fact that that private key can never be compromised. So this is DNS Sec. It's resource record signatures. So a quick explanation. In fact, I'm just going to open up a pre-prepared one so that I don't have to draw it again, because we're getting towards the end of the webinar, and I'm just going to pull across a slide that shows how it all relates together for DNS Sec. Where are you, DNS Sec? There it is, and that's what I want. We're just going to drop that in, and then I'm going to talk about it. Come on, paste, please. Hurry up, we're getting to the end. Good. So here we are. How does it all work? Here is the zone file for rob.com. Inside there, I have an A record. I also have a resource record signature, which is a signed hash of that A record. Now I needed to use a key. To lock the signature. So which key did I use? I generate a pair of keys, a public-private key. I lock the signature with the private key, which means I must publish in my zone the public key. And that's in a resource record, which is a DNS key resource record. And I make that available to the world. So they can then use that public key that I've published in the DNS system. They can always get this public key. This can be taken from DNS. So this is obtained through a DNS query to the relevant zone. So I can make a query to rob.com and say, give me your DNS key that you signed that with. And they'll go, there's the public. If you can unlock it, we use the private. So that's called the zone signing key. And that's the key that is used to sign every record in the zone. But then how do we know that that zone signing key is genuine? What we do is we produce another RR-SIG for the zone signing key, but that's been locked with another set of keys called the key signing key. We publish the public key signing key inside the zone. How do we know that's genuine? Because we've gone to the parent, which is .com. We've taken a hash of that, and we've included a delegation signature, which is a hash of this. And that's signed by the .com zone signing key. How do you know the .com zone signing key is genuine? Because it's signed by the .com key signing key. How do you know the .com key signing key is genuine? Because a hash of that has been placed in the root and has been signed by the root's zone signing key. How do you know that's genuine? Because it's been signed by the key signing key. How do you know that's genuine? Well, you've taken, by secure download, you've taken that public key from the root zone. So you can see that it is a hierarchy of trust anchored at the root. And if I go to the root zone, here is the root zone. And if I go up, here is the SOA record for the root zone. It has been signed by itself. And if we just move down, this is the zone signing public key for the root zone. And this is the key signing public key for the root zone. So if you can unlock using those, you know that they've been genuinely locked using the private zone signing keys. And if you want to see the delegation signers that I mentioned, if we just do a search in here, let's go for UK. Come on, UK, can you come up? There's UK, and you can see there's the delegation signer for UK. That is a hash of the key signing key from the UK zone. So if you go to the UK zone and you take their public key out, you know it's genuine because there is a hash in the root zone of that key, and that has been signed by the root zone. And that is DNS Sec. And I think we've come to the end. Just a couple more things, and then we'll have a couple of quick questions. We talked early on about negative responses. You have to in DNSSEC, you have to make the capability of saying no such name. And this is where this negative security system comes in. Now, in the early days of NSEC, if you requested, you see here is the zone, we've got Baker, Murray, and Thompson. If you requested for Mr. Dobbs, then they would return to you this NSEC saying, well, between Baker and Murray, there are no records. The problem with this is you've just learned that the next valid record is Murray. So by making a bogus query, I worked out that there was a Murray. So I now can look up Murray to get that record. I can then go to something alphabetically just beyond Murray, make a query for it, and they'll return for me the NSEC record saying Thompson. I now know that the next one is Thompson. I can walk through the zone, and that's insecure. But they've improved that with NSEC 3. Now, finally, just this is a zone without implementing DNS Sec. We've got our SOA, we've got our name server, we've got a couple of A records. If I then implement DNS Sec, boom, look how many records I've now added in. I've got the negative response records, I've got the RR-SIG records, and there has to be one of those for every original record. I've got the DNS keys in there, the zone signing key and the key signing key. So when you implement DNSSEC on a zone, it will be a great expansion of the number of records. Here is a query. This is a query for this name, test secret local, and it's saying, by putting an optional record in there, I want DNSSEC. The reply comes, oh, here it is, and here is the resource record signature. So in my reply, I get the original A record and the signature. Now look, it's saying here that if you want to decode this signature, you must use key with a tag of 29374. So I now have to go and do a query for the DNS keys for secret.local, and then they will respond. You can see that one of them is tagged 29374, and that is the key that I can use to verify this signature here. Good. We've come to the end. I've covered everything I promised to cover, and we're bang on time. Holly, are there any questions?
Oh, we haven't. We've got quite a bunch this morning. If you do have any questions, just drop it in the Q&A. But thank you all for joining us. We hope you enjoyed this session. And remember, if you have any other webinar topic suggestions, get in contact with us and we can look into it for you. And also remember, just that quick short survey after you leave this webinar. We'd really appreciate your thoughts and feedback. Both myself and Rob will stay on the call for a few extra minutes if you do have any last minute questions. But if not, thank you very much for attending our last session, and we hope to see you again soon.